Okay, so welcome again to the attendees from outside PRL and inside PRL for this seventh PRL-IAPT Dr. Vikram Sarabhai lecture series. And to begin, I would like to invite our director, Prof. Anil Bhardwaj. Sir.
Namaskar, Swagatam, Abhinandan, very good afternoon to the 7th PRL IAPT Vikram Sarabhai lecture. ये 7 साल का जो हमारा संबंध रहा है IAPT का PRL का और जो क्या कह सकते हैं जुगलबंदी, वो एक अनोखी जुगलबंदी चलती आ रही है 7 साल से। 2018 में प्रोफेसर कमल नयन जोशीपुरा जी ने मुझको बोला कि हम एक नया लेक्चर सीरीज स्टार्ट करना चाहते हैं और IAPT उसमें भागीदार होना चाहता है, बट PRL उसको ऑर्गेनाइज करेगा। तो सडनली हमको क्लिक किया कि PRL IAPT विक्रम साराभाई लेक्चर इसका नाम रखा जाए और 2018 में हम लोगों ने ये तय किया और पहला लेक्चर 2019 में 7 फरवरी को रखा गया था इसी हॉल। एंड उसके बाद से ये एनुअल इवेंट हमेशा इसी लेक्चर हॉल में होता रहा है, इस ऑडिटोरियम में। इसका नाम है KR रामनाथन ऑडिटोरियम, हु इज द फर्स्ट डायरेक्टर ऑफ PRL। और हम विभिन्न विधाओं को जो PRL में, और ये कह सकते हैं विभिन्न एक्टिविटीज़, रिसर्च एक्टिविटीज़ जो हैं, उनके खास एक्सपर्ट्स को इसके लिए बुलाते रहे हैं। और आज जो 7th PRL IAPT विक्रम साराभाई लेक्चर है, उसके वक्ता हैं प्रोफेसर विजय साहू, and he is going to talk to you on a very unique what you call title excuse me, which you will hear from him only because अभी title तो announce हो गया but दिखा नहीं रहे हैं अभी, so which I like very much, you know, his title is very catchy। यार क्या नाम है बता दो? हैं? एक्सपेडिशन, हाँ एक्सपेडिशन मुझे बोल रहा था, एक्सपेडिशन टू एटॉमिक यूनिवर्स। एंड he is an expert in the area of calculations, and he is one of those who extensively uses our HPC computers extensively. So you will hear a lot of new ideas from him of how, what we should say, rigorous, exhaustive and lengthy calculations can be done using the HPC. Regarding IAPT, this is a very old association of India, and we are privileged to have an association through this memorial lecture, Vikram Sarabhai lecture. And we welcome the delegates of IAPT to PRL for this function, as well as, of course, my own colleague from PRL, and all those who have joined us live on the PRL's YouTube channel. So with this, I would like to request the organizers to continue this event, and requesting Bhushit to take care of it. Bhushit.
Dr. Chetan, to introduce the speaker, please.
Good afternoon, everyone. It gives me great pleasure to introduce Professor Bijaya Sahoo, who is a dear friend. Formally, as you all know, he is one of the finest atomic physicists, theoretical physicists of the nation easily. Professor B.K. Sahoo joined IIA Bangalore for his PhD and left for GSI Darmstadt, Germany in early 2004 to complete his PhD. and he got the DAT fellowship. He did his first postdoc at Max Planck in Germany, Dresden, and then worked at KVI University, Groningen, Netherlands, as a project leader on atomic parity violation as a high precision test for unified electroweak theory. Then he joined PRL. Professor Sahoo is working in atomic molecular and optical physics division at PRL. Professor Sahoo has been listed as one of the top 2% scientists world over since 2020. He is a recipient of several awards and recognition that includes fellowships of National Academy of Sciences, the Booty Foundation Award 2018 for Excellence in Theoretical Physics, Astrophysics and Biophysics 2016 by the IPA, then PFI Fellowship from the Chinese Academy of Sciences for the year 17 and 18, Indo-Australia EMCR Fellowship by INSA for 16-17, INSA Medal for Young Scientist Award in 2012, SN Ghosh Award from the Indian Physical Society as the best young physicist for representation. Okay, and then Professor SN Ghosh Award, Young Scientist Award for from the Indian Society of Atomic and Molecular Physics in 2010, and even for the best thesis award in 2006. So it gives me great pleasure and it will be a delight to hear him. I welcome Professor Bijaya.
Slides are put on the screen. So let me first tell that Durga said that his measurements were carried out just before the sleep mode of lander. So since his presentations is over, so please don't go on the sleep mode. So be active. So then only I'll be able to present my talk. Yeah. Okay. Okay. Good afternoon to everyone. So at the utmost, let me thank Professor Anil Varadwaj, Director of PRL, for nominating me for this special lecture, and then the office bearers of IAPT, President Professor Vinod Kumar and Professor Ken Joshipura, and other office bearers for accepting the nomination. And also my other colleagues like Chetan, Professor Minakshi, Vinod Kumar, I know them since 2003. So I have long association with them. So since it's a part of this IAPT lecture, so the mode of lecture, presentation will be like teaching mode. So it's a mode. So I'll be basically talking about one atom, and I presume, or I just try to have analogous view of this like a mini universe, and just while presenting that, hopefully I'll try to convince that. And I also hope that by end of this talk, I'll try to convince you that this atom, one atom itself, it's like it's like natural treasures of many fundamental physics. So so before the actual presentation, I would like to make one declaration that if you want to do atomic physics, so we can use that in two different ways, for in destructive mode or constructive. So my focus is just to present carry out this or to apply this atomic physics in the constructive mode, like making atomic clocks and to understand fundamental physics and so on. So if you go through this PRL home pages of each division, we have 7 divisions. And you see that there are some words that I have highlighted. So these words in one or some way, they are related to atomic physics research. So now all the elements, the atomic systems we know, so they are grouped in the periodic table. So in the rows or columns, if you follow, so almost everybody who has some from science background, even from the high school level, so they know that they share some similarities. And that similarity comes if you follow this periodic table, where the elements are grouped under S block, D block, F block kind of elements. So it shows that So depending on the electronic configuration, which basically describes the atomic structure, so that identifies some peculiar behavior that gives some kind of like identification or some kind of peculiar characteristic. So they behave in the similar way. And also yet they have some different, difference, among, like when you go from one to another element in the same group or something like that, but they have mostly some peculiar character. Now, if we talk about matter, matter means anything you see around, okay, here. So each matter is made up of atoms, and that's why you call atoms as the basic building blocks of matter. So it is like similar to making, like if you build one some like house or something like that, we can consider bricks are like basic building blocks. Okay, so when you put bricks one another, so it gives you a structure. So similarly, atoms forms matter, but it doesn't mean like when you break break the brick, so you can also see further constituents. So similarly, atoms are not fundamental objects. So we can also break atoms. So that means within atom, we also have some structures, or we have more like fundamental particles, like we can have nucleus, and this nucleus consists of protons and neutrons. And these protons and neutrons, they are made up of quarks, up quark and down quark. So when we talk about atoms or nucleus, or in fact condensed matter systems, so we can apply quantum mechanics to study their properties. But if you go much bigger systems like what you see here around, so you can study or their properties using classical mechanics. But if we go towards the subatomic particles like nucleus or protons, neutrons especially, then quantum mechanics itself is not sufficient. So we have to go beyond the quantum mechanics to describe that. And similarly, when we try to understand the properties of quarks at the elementary particle physics level, so quantum mechanics is not sufficient. So we need models or some kind of another theory which is not known. So that is why we use models right now to describe these fundamental particles. And the most successful model what we have so far is called standard model particle physics, but that is only a model. So that means since we don't know the complete theory, we call it a model, but we are still trying to uncover what is the complete theory that can describe the whole thing. Okay, so that is one objective. And even in the end of the talk, so I would like to tell you that whether we can see some kind of such physics, through atomic physics, because atom consists of all these elements. And from the nuclear physics point of view, if anybody is doing nuclear physics, so from their point of view, so this periodic table of what I showed earlier for elements, that is not very interesting. For them, this periodic table is the most interesting. So here, the elements are like arranged in terms of isotopes or the number of neutrons. And what you see, the black dots, so they are the stable nuclei. And above that or below that, so these are like same elements with a different neutron numbers, so isotopes. So they are not stable. Okay. So for nuclear physicists, if they want to understand nuclear structures and their behavior, their properties and like that, so they try to study all these elements and then try to predict many physics. And since the nucleus is a part of atomic system, so that means you can also think that whether we can probe the nuclear structures through atomic physics. That is another objective of this study. So as I mentioned, there are two objectives, like probing some signatures of particle physics and probing some signatures of nuclear physics through atomic physics. Now, before doing that, so let us atomic system, like what is like happening inside that. So as I said in the beginning, or also my title says that I try to imagine this as a universe. So here you can understand, like view that this is a nucleus like a sun, and electrons like planets. So that means this universe is without moon, but you can also consider moon later. I'll show you that how. So if we have structure of atoms like this, then what kind of interactions we expect? Sorry, here. So one is electromagnetic interactions, because here what you see electrons and all these particles, they are charged particles. So this is the dominant interactions inside the atomic system, and all the atomic spectra when we study, they are governed by this electromagnetic interactions, and they are basically between electron nucleus, electron and proton interactions. Right? So most of almost everybody is familiar with that. But in addition to that, So there can be also weak interactions. There are actually weak interactions, and that weak interactions you can see between electron nucleus, electron, and proton, 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 neutron, and so on. But generally, these weak interactions, they are there inside the atomic systems. They affect to the electromagnetic, the spectra, atomic spectra, but their influence is so negligible. We don't generally, mention about that. Okay, so what their effects are there. In addition to that, we also have strong interactions among proton-proton, proton-neutron, neutron-neutron. But what do we do generally when we try to study atomic spectra? So because these interactions are so strong, we cannot include that, if you directly we don't include, while studying the atomic spectra. So we try to study with respect to the strong interactions. So some way we try to separate that. And these three interactions are part of standard model of particle physics. They are fundamental interactions. But beyond standard model of particle physics, there are many phenomena that have been also proposed, okay, by physicists. Like there could be like Lorentz symmetry violations. There are like interactions due to the neutrinos. There could be some dark matter candidates which will be responsible for interactions within the atomic systems. And there could be some additional CP violating interactions, and there could be some new particles which are also responsible for giving rise new interactions. Those we are not aware, but there are proposals, and there are like experiments or people are trying to probe in the particle physics research. So the question is, can we get these signatures through this atomic physics studies? Yeah. So now, if you want to probe such things, so what do we have to do? So then we have to start investigating the atomic structure, theoretically as well as experimentally. So when we try to do it theoretically, so it depends on how you imagine about an atom, how the theoretical atom looks like, and how the interactions are playing the roles. So one simplest structure is as you see here. So this is like you can have a 2D kind of pictures. So nucleus is present here, then electrons are moving in different cells. This could be another realistic view, that is a 3-dimensional picture, or you can have more complex picture like the electrons are moving in some elliptical orbits or something like that with some lot of interactions within that, or even you can think about more complex structure. Okay, so orbits are not well defined and there are strong interactions. And depending on your imagination, how much interactions you want to take into account, I am going to tell you that what these interactions means. And you can also imagine something like that. So here there are strong interactions, a lot of things are happening within the nucleus that also you can take into account. So what we do is when we try to basically study the atomic studies, we start with a very simplistic picture like this. Now the question that like I have already proposed, that can we get some information that is happening within the nucleus or at the elementary particle physics level through starting the picture like atomic structure studies at this level. Okay, so that is the question. And to do that, so let us try to understand the dimension of these particles or this object. So if we imagine atom as a universe, so its size is of the order of 10 to the minus 10 meter. And the solar system like nucleus is of the order of 10 to the minus 14 meter. And within nucleus we have neutrons and protons, they are of the order of 10 to the minus 15 meter. And these like particles like quarks or electrons, as you see that there are very small objects. But here it says it gives a limit. Okay, it doesn't give the actual value. So that is because we do not know the exact size of these electrons and quarks. So their values are predicted depending on the models. Their values like are predicted differently, and that also we can prove using atomic physics studies. And now, where is the challenge to actually prove these particles directly or their size? How to why there's a challenge to measure their size of these particles. So the challenge is it's based on this relationship, Heisenberg's uncertain principal relationship. What it says that delta x, uncertain in the position and momentum, is a constant. So that means, so if you want to measure a small quantity, so it's a size or position, so you need very high energy experiments. So that means if you want to do experiments for atoms, because the size is bigger, so the energy facility that you need at the EV level, that means you can do using tabletop kind of facilities in the laboratory. And if you go for highly charged ion, where the orbitals has shrunk because of the nuclear size is much bigger, so there you have to go the energy facilities like some experimental facilities of the order of keV, kilo electron volt. And if you want to probe nuclear structures, so you have to go energy level, order of the order of mega electron volt. That means you need some kind of mini accelerator kind of facilities. And if you want to go below that, like beyond that means quarks or even much fundamental particles like that, so you have to take the help of the bigger accelerators like that is available in CERN or something like that. Okay, so that is the challenge. But what we are trying to do, so our aim is to probe this kind of physics at this energy level. Okay, indirectly. So maybe it's not possible to probe everything, but at least we'll complement to certain findings. So that is what our objective. Okay, so what we want here for doing atomic physics, we basically going to apply only quantum mechanics. Whatever you like, quantum mechanics as the BSc or MSc level. That's all. You don't need any models or something like that. So what is quantum mechanics? In quantum mechanics, we define states of a system, and that is basically given by wave function using some quantum numbers. Like basically it means, like Durga mentioned, that our directory is everywhere. So quantum mechanics exactly says the same thing. So that means quantum mechanics says that there is a finite, there is a possibility of finding each particle that, at each point, if you use, this kind of concept. But when you do measurement, then it collapses, the wave function collapse. You see, that person or that object, or that observable, there. So like, since we see our director here, that means there is 100% possibility that he's here. So he's not, present everywhere. Okay. So that is what the quantum mechanics is. But how we get this wave function? So we get this wave function by solving this simple equation called Schrodinger equation, Si equal to E psi. And equivalently, some people use, instead of wave function, they use density functions. It's equivalent because it's related to wave function, and one has to solve this wave function. So that means if you know your Hamiltonian, and this is the energy eigenvalue, so you can solve this equation, and you know your wave function, then you know everything about that system. So what is Hamiltonian? Hamiltonian is nothing but the total kinetic energy of the system plus the total potential energy of the system. So if you know these two parts, that's all once you define your Hamiltonian, then you can solve this equation. If you can solve this equation, there could be also challenge. Even you know the Hamiltonian, but it's not always possible that you can solve this equation. That will come back later. And so then let us say for some observables, like let us say we got the wave functions, and then for each observable in physics, we associate that with some operators. And if that operators commute with the Hamiltonian, so then those operators or the corresponding properties also can be described using the same wave function. If not, if this is not commuting, that means then either the operator has to be written in terms of some operators which will commute with the Hamiltonian, or the wave function has to be, or the wave function of operator A has to be written as a linear combination of the wave function of Hamiltonian. That's all you have to do. So once we get these wave functions, we can solve, all, like we can find out all the properties. And what are the observables? So these are the observables in quantum mechanics. So that means the probability of finding the particles, mod square, mod psi square, or expectation value of some operators, or something like this, you can have. So this is the, these are the observables. When you say measurements, in the measurements, like if you want to correlate that with the theoretical quantities, so it will come like this. And in terms of density functions, it will look like that. Now let us understand, now in the atom systems, so how to write down the Hamiltonian, what is the actual complete form of the atomic Hamiltonian, and how much we can solve from this Hamiltonian, and where is the challenge. So in the non-relativity form, so if I imagine that the atomic system looks like this, it's like some electron cloud and a lot of interactions within that. So then the total Hamiltonian can be written down as the kinetic energy of the nucleus, then the kinetic energy of the electrons, and electron-nuclear interactions, potential energy, electron-electron interactions, so on. And in the relativistic form, so you can have some extra contributions, like there will be corrections due to the rest mass corrections to the electron as well as the nucleus, and there will be some self-energy corrections to the electron orbitals, and there could be higher order contributions from here, and electron-nuclear interactions and vacuum polarization effects, again nuclear potential effect, it's a higher order corrections, and you can also have higher order vacuum polarization effects. Then, so these are the the interactions between electron and electrons because of the exchange of photon. So when you consider transverse photon, longitudinal photon between electrons, the exchange between two electrons due to the longitudinal photon, that gives us Coulomb interaction. And due to transverse photon, we get bright interaction. This is a higher order corrections only in the relativistic theory. In the non-relativistic theory, you only consider Coulomb interaction. And similarly, you can have 2 photon exchange, 3 photon exchange, and so on. And all these possibilities quantum mechanics allow. So if you want to do more and more accurate calculations, so if you can include all these interactions, then you get the exact, contributions to your calculations. If you then otherwise, if you make some approximation, then you get approximate solution. That's all. And depending on the level of precision or accuracy you want, so you can make the approximations, in your Hamiltonian, and then get the wave function, and that is how you can, describe the atomic properties. And you can also have fine structure level, splitting, that that anybody is doing this astronomy, astrophysics observations, then hyperfine splitting. And you can also, this is due to the magnetic dipole hyperfine splitting. You can have electric quadrupole hyperfine splitting, octopole, octopole magnetic dipole, octopole moment contributions due to the hyperfine interaction, and so on. And along with that, so all these interactions are due to the electromagnetic interactions. But if you consider the other interactions, which I had mentioned earlier, you can also include the weak interactions, then the additional CP violating interactions or CP violating interactions, Lorentz symmetry violating interactions, strong interactions, and also if you expect that there are some contributions coming from beyond the standard model of particle physics. So depending on what you are interested in, you can put those additional interactions, then you can prove those kind of properties. Okay, so there is another part to that. So this electron nucleus, this atomic system, which has electrons and nucleus, that you can also have, there will be some kind of equivalence between like Sun, Earth, two-body kind of problems. That means you can think that this nucleus is like Sun and electrons are like Earth. Okay, so the previous Hamiltonian, the form I showed you, that is written by assuming that the nuclear mass is infinite. But here the nuclear mass is not infinite. So if nuclear mass is not infinite, so this nuclear mass will affect to the energy levels. So there will be also some corrections to the potential energies, and that correction we call this a mass shift effect, which will give corrections to the kinetic energy term, which we call normal mass shift. And it will also introduce another kind of two-body interactions, that is the interactions between the moment of two electrons. And this is known as specific mass shift corrections. And if you are interested to study the isotope, like the energy difference between two isotopes, so it is going to contribute because it depends on the nuclear mass. And similarly, when you go from one nuclear, like one isotope to another isotope, their size also different. Their sizes are different. So that means the potential energy also will depend on the nuclear potential energy. That will depend on the nuclear charge radius. So there will be another corrections to the potential energy due to the finite size of the nucleus. Like in the hydrogen atom, you generally consider you assume that hydrogen atom nucleus is point-like, but it's not point-like. So if you assume it's a finite charge, so this will be like this potential energy will be written into some constants which will depend on the electron wave functions times the radius of root mean square radius of the nucleus. So now let us see what is the challenge then. Why we sometimes try to drop some of the interactions while solving the atomic, that Schrodinger equation. So now in the textbooks you will always find that it talks about a hydrogen atom. And in the hydrogen atom, basically it considers kinetic energy term and then the nuclear potential energy term. In the relativistic form, you can also have reduced mass corrections, rest mass energy correction, self energy correction, and vacuum polarization effects. So in the textbook, generally it gives the solution for only considering kinetic energy term and nuclear potential energy term. But if you consider all these things, systems also, you can get the exact solution. That everybody is familiar with that for a hydrogen atom, we can solve the Schrodinger equation exactly. But that you can solve exactly because you are not considering that finite size, the nuclear mass effect. We assume that nuclear mass is infinite. And what it offers that each states, they are described by some quantum numbers like principal quantum number, angular quantum number, parity, and so on. That's what from the hydrogen atom problem you learn that. And all the potential are pure symmetric, spherical symmetry. So everything is expressed using spherical coordinate system. So all these states, atomic states, are described using these quantum numbers. In fact, this concept also we borrowed to the heavier atomic systems. So all the electronic structures, they are described using atomic levels, and with this using these quantum numbers. So using these quantum numbers, like each element of that periodic table, what I mentioned when we have grouped, so that is characterized by from this electronic configuration. That means it gives the Aadhaar card, this one to each element of the periodic table. So you will get all the information by just knowing these quantum numbers or electronic configurations. Okay, so where is the challenge? Challenge here. As soon as you start considering electron-electron interactions, the two-body interactions part, so there is the challenge to solve that Schrodinger equation. So what happens in this case, that when you try to solve the wave function of one electron, it depends on the wave function of the other electron. So it's a two-body problem. So that you cannot solve. So you have to make some approximation there. So that is why, apart from hydrogen atom system, you cannot get exact solutions for all other atomic systems. But then when the number of electrons increases, then it becomes even more challenging. Okay, to get these wave functions more accurately, because depends on how much you have to take into account these electron-electron interactions and how much you can neglect. Then let us say that you can solve this hydrogen atom, the atomic spectra, or you can get more accurately. Then where you can apply? You can apply, you see, in all these studies, like identify interstellar objects, whatever, like we are talking about Chandrayaan data. When you analyze, you need this knowledge of this data, and analyzing Aditya L1 data. And apart from that, also we can apply them to to set up this atomic clock kind of experience, where unless you know the atomic energy levels precisely, you cannot set up the experience, like cannot find out which laser has to be used and how the setup has to be done, how clock frequency has to be measured very precisely, or like if there are shifts because of the lasers and all this. So all these information if you want to know, so you need to know the atomic spectra or their properties very, very accurately. So that's why only few atomic systems are being considered for atomic clocks, but otherwise in principle, theoretically, you can use any atomic systems for atomic clock purposes. So even how the laser works, and also to find out that which atomic systems can be considered for building these qubits for quantum computers, and also like when you talk about that which detectors are suitable for some measurements, like even to detect neutrinos. So they are decided by from the knowledge of this atomic spectra. Okay, so where is the role of atomic many-body method or theoretician? Like as I said, you see the periodic table I had mentioned. So that only talks about neutral systems. But if you try to ionize them, and even these ionized atomic systems, they have isoelectronic configurations with some other elements, but their energy level structure can be completely different. And also, it's not possible that each time people can measure and find out the energy level structure, because if you consider all these elements and start ionizing, there could be many possibilities, many possible atomic systems. So there, the atomic, like physicists, if they, theoreticians, if they have their methods and they can predict these values, then in many cases it happens. First, the theoretician, they predict them, then so they try to guide the experimentalist in which direction they have to perform the experiments. For example, if I tell you here, like the hydrogen, in the hydrogen atom system, the energy level structure or the orbital leveling goes like this. But as soon as you go to the highly charged ion systems like uranium, hydrogen like uranium or something like that, so there is a change, there will be change in the energy level structure or the like positioning. And this ordering is known as Madelung ordering, and this is known as Coulomb ordering, because in the highly charged ions, the relativistic effects play prominent roles. Because in the highly charged ions, the like electrons will be revolving in a very contracted, like small orbits. So it will revolve with the speed, almost like with the speed of equivalent to the speed of light. So the relativistic effects are quite large, and also the Coulomb interactions, like electron-electron Coulomb interactions, are quite prominent. So to predict these energy levels in the highly charged ions, and also, I don't know whether you know that or not, if we use a non-relativistic theory, like to predict or to calculate the properties of gold. So if you use non-relativistic theory, so its ground state configuration will come out to be like, it's equivalent to the silver atom. So that is why there is a famous saying in the non-relativistic theory, gold is silver. So unless you use a relativistic theory, you will not get the proper configuration. Okay, so that's where the relativistic effects play, so that is where our role comes. Okay, now I'll give you one typical example, like what happens. Now let us consider this 5d5 orbital in the hydrogen like ytterbium, and within, so let us find out its electron density within the nucleus. So as I said, it's a quantum mechanics. So that is why, because of quantum mechanics, there is a finite probability that the electron can be present within the nucleus. And we can find out its density within the nuclear region. So it's within the nuclear region, and it goes like this. Now, if you go, if you now consider like ytterbium ion, but then I consider that this electron-electron interaction is like some average potential, like some screen potential. I don't take into account this electron interaction exactly, but I make some kind of average. It's called mean field approach. So then the wave function or density looks like this. But in the actual ytterbium ion for this orbital, so the structure, electron wave function, behaves like this. So unless you have proper or accurate many-body method, you cannot get this kind of behavior. Now, what is the consequence of that? Now, let us say that if you want to find out this hyperfine structure splitting, and that defines this by this constant A, magnetic dipole hyperfine structure constant. So in the H-like systems, so this value is like with a positive sign. And with mean field approximations to ytterbium ion, you get this. But when you consider the exact theory that we have, you get -64, where the experiment value is exactly -64. Okay, so even some of this many-body theory cannot even predict these kind of things. So what it means that, so these atomic platforms or many-body theories are also like, it can test the quantum. They are very good platforms to test the quantum mechanics. So that means it says that unless you have the wave functions accurately within the nuclear systems, within the nucleus, atomic nucleus, you cannot describe some properties. And also, if you want to predict the lifetimes of atomic states, unless the wave functions are accurately determined outside the nucleus, you cannot estimate the atomic lifetimes accurately. So that means it says that the electron is present starting from the nucleus, within the nucleus to outside the nucleus. So there is a probability, right? So everywhere. Okay. So the other thing is the field shift. As I said, if you go from one isotope to another isotope, since there is a size difference, nuclear size difference, so you'll see a potential energy difference, and that is given by F times the delta R square. Now what people do, so experimentals, they measure this energy shifts by measuring the energy level difference between two isotopes, and very precisely, because these effects are very small. And theoretically, we can calculate F because that depends on only electron wave function. So if you combine these two, we can extract these values. So what is the consequence of that? See, the consequence is, so this nuclear physics people, when they try to probe the nuclear structures, so that information they get from the values of delta R square. So here, so from this measurement, which was carried out at CERN, because here it involves a lot of radioactive isotopes. So this is the measurement which predicts that our delta R square values, like this. And then in the nuclear structures, why this measurement, like this is published in Nature Physics paper. So why it was important? Because earlier some of the nuclear physics calculations or nuclear calculations, they predicted that the potassium isotopes, they have some kind of magic structure. But when this calculation, or when we did this probe, we found that there is no such magic structure. Okay, so that helps nuclear physics people to validate their theory. And also in another case, like it was predicted that some nuclear theory predicted that these tin isotopes, they have double magic character, and some theory said that no, that's not correct. So they did not accept that. So our study recently showed that yes, indeed it has double magic character, this isotopes has. Okay, so that may, and also recently this is submitted. So we have predicted the delta R square values of ytterbium isotopes from doing this kind of calculations by combining our calculations with the measurement of isotope shifts. So you see that both are equal. It's not only the measurements are equal. Important. So what it means that, so our this kind of studies from atomic studies, we can give precise values of nuclear charge radius, and also it helps to describe the nuclear structures, and it helps to validate the nuclear theories. There is also another prediction that there could be a new kind of interactions between neutron and electron. Okay, so neutron is a neutral object. So there is a like prediction from beyond the standard model of particle physics that some kind of bosons are existing. So they give additional contributions to this kind of nuclear interaction. If so, so that means you can see this like differences when you try to measure the energy difference between two different isotopes, because they differ by the number of neutrons. And if you do that in the potential energy, energy, they will get another correction. And from that correction, people are trying to predict, extrapolate the mass of this new vector boson. Okay, and also, there are many nature papers and PRL papers on this. So I'm trying to study that. I have not initiated, but what I'm saying is people have been probing such kind of things, and there are a lot of nature physics, nature paper, on this. And these are all the recent proposals. And there is some new phenomena now I'm going to talk about. So the standard model of particle physics says, or it has been already proved, that this electroweak interactions, electromagnetic and weak interactions, they are actually one interaction. Okay, so these are two different manifests. So what we generally do, we only consider electromagnetic interactions, and these are basically mediated by photons, and the strength goes as with the number of charged objects inside the atomic systems, and parity is a good quantum number here. And all these interactions are actually controlled by these electron-proton charges. But if we take into account weak interaction, so that can happen because of the exchange of jet particle between electron and a nucleus. So that will be, so that strength goes as ZQ, that with the number of, Z means number of protons in the system. And if you take into account this, then this atom, atomic states will not have a particular parity. So it will have different mixture of different parities. That means this orbital quantum number L, what you used to use to describe the atomic states, you cannot use anymore. And it gives a nuclear kind of properties called nuclear weak charge. And since this interaction goes with the ZQ, so we can only see them in the heavier atomic systems like cesium, barium, francium, radium kind of systems. And this nuclear charge can be written as in terms of this coupling coefficient between electron and up quark, down quark like this. And in terms of this Weinberg angle, so we can express, this nuclear weak charge in this form. This is N is the neutron number, Z is the proton number. So that means for each element in the periodic table, you can find out what is the nuclear weak charge. And these values are known within 0.1% accuracy. Now, if you assume that there are physics beyond the standard model of particle physics and they contribute, so then you can, there are like proposals that not only one jet boson, there are like different kind of jet bosons or dark photons, they can contribute, and they will they will be responsible for this kind of weak interactions, and they will also contribute to this nuclear weak charge. So if you want to prove that, so if you can extract this value from atomic study, and then if we compare with the standard model value, if you see some difference, that difference will tell you that whether there are really physics beyond the standard model of particle physics or not. So that this kind of experiment was done in cesium. So now how this can be measured or how this can be obtained. Now let us consider two atomic energy levels of same parity. Now if you only consider assume that there are electromagnetic interactions, so electric dipole transitions are not possible here. But if there are weak interactions, then there will be some contributions from the electric dipole transitions because parity is violated. And that cannot be measured directly because it's a very tiny effect. So that can be measured along with by interfering with another forbidden transition like magnetic dipole or electric quadrupole transitions. Like if you consider transitions like S to D, so it can be this electric dipole transition in the presence of parity violation can be interfered with electric quadrupole transitions, and this interference pattern can be measured. And once, so this was measured in cesium by Carl Weinman group. So he's a Nobel laureate. So they had measured this E1 transition amplitude in the presence of parity violation and interfering with some kind of Stark effect, and that measurement was within 0.5% accuracy. And this measured quantity can be expressed using some QW times this theoretically you can express like that. Now, if we can calculate this quantity within 0.5% accuracy, so by combining these two, we can extract QW value. So this way it will be model independent. So this calculation is done using quantum mechanics, that is model independent. This is a measurement, that is model independent. So this quantity will be model independent. So this, when we did that, so then we got this QW value by combining our calculations with that measurement is given here, and this is the standard model predicted value. So from there we got, so we extracted a lot of quantities, like we also extracted the mass of dark photon and some extra bosons and like that. Okay, so that means you can probe a lot of fundamental physics from the atomic structure itself. So there is another concept that you know that what is electric dipole moment? It is the charge separation, and when there is a current revolving like this, it will give us the magnetic dipole moment. And if you have some current like this, toroidal current, it gives us toroidal moment. So there is a proposal in 1959 by Electroweak and BSM. They said that due to weak interactions within the nuclear system, you can expect that there will be a toroidal kind of currents within the nucleus. And that can be proved from the parity violation measurement. And again, with the combining with the atomic theory. And that's what we had done recently. But this value shows that actually the nuclear anapole moment exists. And as a, by the way, this is like it's a proposal, and this moment is a fundamental quantity. So far, we don't know actually exist or not. If it exists, so it will be considered as like another fundamental quantity of the nucleus, like mass or charge. Okay, so that is what we are trying to prove, that whether such moments exist in the atomic nucleus or not. So what we see from here that okay, it supports that this to this proposal, but this calculation or this obtained number doesn't agree with the nuclear calculations. So that's why there are a lot of debate going on. But hopefully in the future, if more experiments are repeated or more studies are done, so maybe we'll try to establish that whether really there is nuclear anapole moment exists within the atomic systems or not. But if this is established, this will be a new property of of atomic nucleus. There are also like we can study CP violations like in the atomic within the atomic nucleus we have strong interactions between neutron, proton like that by the exchange of pi photon, pi meson. And because of that, so there could be also some CP conserving and CP violating interactions. And such interactions, if you take into account, and if they interact with electron, then the atom can have dipole moment. As you know that atoms do not have dipole moment. But if there are CP violations with the atomic systems, then that can give you permanent dipole moment to the atomic system. Okay. And similarly, if there are like interactions between electron and neutron due to exchange of some CP violating particles, so that can also give you electric dipole moment of atom. And again, when we say electron, and many people may be thinking that this is just like a point-like object, but it's not a point-like object. So it's just a like cloud. The real electron means it's like moving with a cloud, and that cloud, like it will have contributions from electromagnetic interactions as well as CP violating kind of interactions. Now, depending on what kind of model you consider, then what kind of CP violating interactions you consider, it predicts a different kind of sizes, nuclear sizes, which I had mentioned earlier. And this or even for quarks also it's a similar thing. So if you want to predict, so that is we call the electric dipole moment, which is ER. So that means if you find out the electric dipole moment of electron, then you can also find out the size of the electron. And that also we predict by doing this nuclear studies and atomic calculations and atomic experiment. So we have put constant on the idiom of neutron, proton, and then of quark. Then there is some parameter called theta QCD parameter and electron idiom. And here the standard model values from the particle physics, and you see that there are a lot of variances. And particularly, if you look at this value, it says that this value can go from 0 to 2 pi, but there is a strong constant here, and it's known as strong CP problem. So, and also for electron idiom, you see that there is like 9 orders magnitude difference. And this is what the uniqueness of this atomic, physics study, that gives to the particle physics, community. And also, you can assume that there could be some kind of dark matter candidate, exchange between electron and neutron. That contribution also we try to prove and try to put the constant on its mass and the coupling coefficients. And this is another thing that proving local Lorentz symmetry violation. So there is a very beautiful experiment was done, like it's like equivalence to Michael Morley type of experiment. So where 2 calcium ions are considered trapped, then the interference between the Mj equal to plus half minus half and Mj equal to plus 5 half and minus 5 half of these calcium ions were interfered, their energy levels, okay, of d5 half state. And that interference was, then the influence of magnetic field with respect to the direction of sun. So that was proved. So that by varying the magnetic field, this one with respect to the direction of sun, and then some signature of this local Lorentz symmetry violation was tried to understood. So what is Lorentz symmetry violation? What it says that when you carry out measurement at any frame of reference, so this should be invariant. But if there is a local symmetry, Lorentz symmetry violation, so you will see some variance. So that is what it was like. By again combining with this measurement with our calculation, we extracted some quantities, and that quantity is related to this signature of local symmetry violation. So there are many such aspects. Like for example, you also know that these atomic energy levels, they are also functions of fine structure constant, and there are theories which predicts that these fine structure constants varies over space and time. So that means when you will do this atomic spectral measurements over different space and time, you should also see some signature of changes in the atomic energy levels. So that can also be proved, and people are trying to probe by through that measurement of atomic clock frequencies. And also people are also trying to probe that whether the mass of neutrino, the neutrinos are Majorana type or Dirac type. There are also experiments set up in Japan to probe this kind of thing. So there are a lot of such things can be probed using atomic systems. So that's all I just wanted to talk today. Now let me come to the conclusion. So now, as I said, that atomic systems are the natural laboratories to study many fundamental physics, and general approaches of atomic methods I just pointed out. And I just mentioned about how to probe nuclear structures using isotope studies, and inferring existence of some new kind of vector bosons and atomic parity violations and relation to BSM physics and CP violation effects, Lorentz symmetry violation effects, and so on. But behind all these things are to carry out all these studies, one has to develop, along with high precision experiments, one has to also develop accurate relativistic methods. That is what I'm doing at PRL. Okay, for this I also have many collaborators, mostly from abroad, and he's Ronald from MIT. He's experimentalist, does all these isotope shift measurements, and then Anders experimentals from France. He's from Sweden. He's from Nice University, from Sakemi, from Tokyo, Riken from Tokyo University, and then he's from nuclear physicist from Germany. He's Ben, again particle physicist from Israel, and he's only one atomic theoretician who is collaborating with me recently, and he's astrophysicist from France. And my students, and this is what Professor Anil Varadaj has mentioned. So without this, I cannot do a single research in PRL. And that's why I'm not going away from PRL. And thank you very much.
Okay. Thank you, Professor Bijaya, for nice talk. And now we move forward, proceed to the other part. For question and answer, I would like to invite Professor Vinod Kumar. And before we felicitate the speaker, I will request Professor Vinod Kumar to share something about IAPT, IAPT RC7, and how people sitting here can be a part of IAPT team. Sir.
I think it is not fitting very much at this juncture, because no, people are truly waiting for some of the interaction with Professor Sahoo. So maybe after the interaction it would be appropriate. And we have been, anyway, IAPT is known this institute for many years. 7th year we are running this. And we are very grateful to PRL, the director, for continuously doing this lectureship keep alive. So I think it is better we will invite some questions and interactions with the audience. So any question, any interactions, any comment?
It was too heavy.
No, let me tell, let me ask. Yeah. Probably maybe to initiate, somebody should initiate. So many interactions. Anyway, there is always a talk that atoms within atoms. Yeah. The whole universe you can see within the atom itself. So can you say something about the present artificial atoms, where many of the complications can be avoided? Yeah. So, for example, that is very much relevant with reference to the quantum technologies which are coming up.
See, artificial atom means is like constructing new kind of interactions. Okay, like by applying lasers and like that. For example, in the cold atom systems, here we are talking about electron and nucleus together as one atom. So there, each atom you can view like a single particle. So it's not like you think that within that atom there are electrons, nucleus, like the way we thought about that. So you consider atoms, then you cool them, then depending on the structure in which way you place them, depending on the dimensions and the interaction strength between horizontal, vertical, and all these directions, you can create or you can manipulate or artificially you can generate new kind of interactions, and then you try to study the quantum behavior. That is what we call phase transitions, quantum phase transitions, and like that. So those kind of properties are being studied. So that is known as
artificial. Also, there is a talk of customized atom. These are all some of the phrases that is you can see. You can customize your atom.
Yes.
Maybe in a way how you manipulate and
so again using the lasers. When
Okay.
you say hopping
So-
like with a different structure, 3D,
Right.
and all the things,
Yeah.
you can make that structure. Then the effective potential. So you don't see within atom what is happening.
Yeah.
Just see that within one atom to another atom. That means one element to another element. How the interactions are happening. So this is like fermionic type of interactions or bosonic type of interactions.
Right. Also, recently there is some experiment being done in the atomic physics. See the effect of gravitational effect. So that's also some of the. You may talk about.
So using rubidium atom, so people have done this measurement of capital G. So that is the gravitational interaction strength. That G, if you study Earth, Sun interactions, so the capital G comes there, right? So that value of G, that has been measured in China. They have recently they have done that measurement, and even a small G value also people have done the measurements. So those things all, because it requires all the high precision measurements. So what they do is they create like a cloud of atoms, then they pump them. What is that called? They throw them, and then allow them to fall freely. Then they try to measure this one, and these are very tiny, very sophisticated kind of experiments. So they do that underground. So where the magnetic field and all the things will not.
Okay, thank you. I would.
Okay, Bijay. So very nice talk, and you have very comprehensively covered various aspects which you are taking into account while doing all the atomic structure calculations. My question is in the context of this new point, gravitational effect, gravitational energy effect, and also particularly from the observational point of view. As you know, we are doing X-ray observations of various astrophysical objects, and particularly compact objects like black holes and neutron stars. Okay. And then in the very close vicinity of these objects, we are observing some atomic lines.
What is that?
Atomic lines, I mean, transition lines.
Atomic lines.
Now, so when we are taking into account this gravitational force, which is like much higher gravitational force in the close vicinity of neutron star, what level of influence on this line energies do you expect? I mean, is it
Here
same
it's
as-
completely negligible. Because see, I even measuring the weak interaction itself, which is of the order of 10 minus 13 or 14 with respect to strong interaction, that itself is challenging. What you are talking about is gravitational interaction that controls our
attraction? What I'm saying, within a strong gravity, assuming the same atomic structure for a given atom which is on terrestrial condition versus, let's say, on neutron star, what would be the difference?
neutron star,
between
there will be a very strong effect. So then if you, but only gravitational interaction, if you, like only you want to analyze that part, I don't know how much that will contribute, but in the neutron star, so there will be strong magnetic field effects and electromagnetic interaction.
Yeah,
That is,
Maybe the atomic structure itself at the neighborhood of these very strong
yeah.
gravitational objects is still need to be studied. It is
Yeah,
not, yeah.
but there
So if
Maybe
we,
can
then we
also
cannot
calculate
compare in
how
that
to
sense.
calculate that. See, many times what do we do? If there is a tiny, tiny interaction, and then you see in the background you have strong interaction. So generally we try to only probe that tiny effect. Then we somehow try to cancel out that effect of that strong interaction. So here also maybe probably it will be done like
Yeah,
that.
so basically what I'm trying to say is that this is another avenue where there are some observational potential where these things can be tested. So maybe I think you can.
Maybe that is a
whether
good
this can be
suggestion. Yeah, maybe.
applied to those
Yeah, I can
conditions.
consider that. Sorry, I mean, some people may not be able to hear me. Yeah, so there is one.
back behind.
So if you change the temperature of a material, right, you see a lot of very interesting phase transition. So now if you consider an isolated atom and you change the temperature, what you will see?
Oh, you see a lot of changes, the same thing. So temperature means it will again change the atomic spectra, but again, whether this like temperature again weak, controls weakly or strongly, depending on that, one has to do the modeling. It's not that straightforward answer that with the temperature, how you'll see the, this one. So how much it will, there are models. If it is like weak, temperature like cold atom kind of things, like few nano Kelvin or something like that, it won't change and make much changes. But if it's micro Kelvin, this one or something like that, you'll see a lot of changes. For that, you cannot use this kind of theory. So for them, so that's why such kind of things cannot be exactly solvable. So some people use models, but again, there are again predictions. So here itself we have challenge. But if you talk about those things like temperature or even so those things are very complicated. It's not that straightforward.
Students, I hope there are many students. Not many? Oh, I mean, research scholars are also students in that sense.
There is one.
So please.
A great talk. I have a question that you showed in the yttrium like ions and atoms. So you showed different.
Yttrium is different.
So yttrium. Oh. So you showed different types of theories, approximations. So for the like, what kind of things were incorporated in the exact theory so that it was matching the experimental?
Yeah. So it's a very tricky question, but nice question. But I don't know how many people can understand. See what happens like when you saw this electron-electron interactions. So those who are familiar with this field theory, like particle phase people, they can each interaction I was talking about self-energy correction, vacuum polarization, or like that. So you can visualize like that. So particularly why I highlighted this example, like for example, you consider s orbital or p orbital, you won't see such large differences in the sign or something like that. So it particularly happens in the d phi of states. So that is because there is something called core polarization effects that is responsible for this. What it does, so that it excites the 5D electron and takes it to the virtual electron. That is again coming back to some kind of core electron. Again, that goes to the valence electron. So that happens because of that some nuclear kind of interactions that is responsible for that. So it's known that means the core electron is polarized. Okay, that is why it's called core polarization effect. So that those who are interested in to learn many-body theory like that, for them it is interesting that why it is happening. And not all many-body theory can predict that. Only some people may be using configuration interaction method, I think, in this audience. So those kind of methods cannot, explain this kind of thing.
So no more.
Yeah.
Would like to say something. Or you can put some comment also. Invite somebody I want to ask.
Thank you very much. Very nice lecture. This was the 7th PRL-IAPT Dr. Vikram Sarabhai lecture. Last year we had the 6th lecture that was given by atomic physicist Professor Nigel Mason. Actually, the series, the annual lecture series started with Professor Anil Bharadwaj talking to us on Indian planetary programs and that. So in 2019, and then next was by Professor R.D. Deshpande on aspects of hydrology and water management challenges. Then Professor Abhijit Chakrabarti talked next year about the exoplanet systems. We had a lecture by Professor Pallab Raju also, by Mrs. Shubhavati Goswami on neutrinos. And so year after year, very interesting aspects are considered, right from macro world to astro world to micro world and connecting things. It's all about physics. Thank you very much for the annual lecture series. And now, Professor Bijaya Sahoo, on behalf of the IAPT, we wish to present you a novel system of Avogadro number of atoms, very nicely arranged and beautifully layered with another system of atoms. And let me try to find out. It's here. Oh, yes, it is here for you. So, our great pleasure. Our great pleasure. Thank you. Thank you. Thank you. We'll give you the. Thank you so much, Dr. Bushit.
You can go.
Okay. Okay, if you don't have any more questions or doubts or any interaction that you can have with the speaker, Bijaya Sahoo, I would like to say a few sentences about IAPT. IAPT just completed 40 years of its existence. In fact, it has started in 1984 with very few physics teachers or physicists. And then it has evolved now into more than 10,000 life members, spreading all over the country as well as few hundreds now spreading abroad. So I think it is evolving, and all people who are working, who are associated with physics, so it is the Association of Physics Teachers, all are basically teachers, one or the other way. Whether you are in a mission, you need to teach with some of your associates, or you are in a scientist, again you will have teachers, you have to guide your students. So in various ways, all those who are associated with physics can be the life member of this association. This year, particularly because of the declaration of 2025 as the International Year of Quantum Science and Technology, many activities every month, every week, sort of activities are going on under the IAPT umbrella, spreading throughout the nation. We hope many such activities can be continued within Gujarat with the association of every one of you, everyone who is working, who is teaching, who is doing research in physics can be associated with these activities. And with this brief, I don't want to say many things. There are many examinations at the national level are being conducted for the students at the school level, at the PG level, at the UG level, as well as for research level. I hope competitions of the innovative experiments are extended from all the school level to teachers. Even teachers can compete for innovative experiments competitions at the national level. And many of these awards are being recognized by various institutes. And some of these winners, toppers, are being directly recruited as research scholars in some of the institutes. So these experiments or these competitions undertaken by IAPT is nationally recognized. And many of the school level, they are directly being trained for competing at the international Olympiads. And many times, not only for physics, it is being conducted for biosciences, astronomy and astrophysics, as well as on other subjects like chemistry. They are being conducted with the associations of chemists or the biologists, and then it is managed by IAPT, and then they are being separately trained for the Olympiad competitions. So with this, I think IAPT is doing a great job. Apart from this, one should also note that recently there is a trend of students, maybe after the 12th standard or before even 12th standard, they are afraid of choosing physics. Physics is such a wonderful subject. which is useful everywhere. Without physics, no biology can come up. I mean, biological developments, latest advancement may not be possible. Even in the one is talking about, the quantum technologies that one is talking about, every day, more than 100 papers are coming on these technologies. Every day, if you see, search. And all those people who are working behind it are physicists, basically. So without physics or physics background, it's very difficult to cope up at the international level. So the recent trend of students not really opting for physics is a real challenge at the national level as well as at the international level. So IAPT is striving very hard to make this point clear to the students and teachers at the school level, starting from school level, and to see that maybe when our quantum missions of our nations are at the level, at least we should have people, we should have manpower who can be, you will be able to digest and understand and operate and can create our own missions, our own technologies. Even quantum missions and technologies are very well useful for your space studies as well. So I think we are all bothered about this issue, and then we look forward, every one of us, to work to encourage our next generation, the school generations coming from schools, to opt for at least science, technology, engineering, and STEM. I will say STEM, even physics should be included, not in the larger sense of science. So with this, I stop here and then probably will conclude with the vote of thanks by Punit Sutar. Thank you.
And I would also like to add that today's lecture was also a celebration of World Quantum Day, which is falling on 14th April.
The IAPT exams are held in various levels, as I said, mentioned. The students who perform well in the IAPT examinations are trained further, trained harder, and they are sent up for the Olympiads, Junior Science Olympiad, Physics Olympiad, in other subjects also. And very happy to tell you that our students always win medals. Always, every year they win medals. तो हमें तो मेडल जीतने की आदत हो गई है. That is a kind of pride we have. Thank you. Thank you.
Good afternoon, respected dignitaries, esteemed guests, or colleagues, and dear participants, both present here and joining online via YouTube. It is my great honor to privilege to deliver a vote of thanks at the conclusion of the 7th PRL-IAPT, Dr. Vikram Sarabhai Lecture 2020-25. First and foremost, I extended our heartfelt gratitude to our distinguished speaker, Professor Bijaya Sahoo, for his enlightening and deeply engaging lecture on a brief expeditions into an atomic universe. Your insight into a fascinating world of atomic physics have left us inspired and intellectually enriched. We are deeply grateful Professor Anil Bhardwaj sir, Director of PRL, for his constant encouragement and support for fostering academic excellence and outreach. Our sincere thanks to also goes to Professor D. Pallam Raju sir, Dean PRL, for setting the tone of this session off so beautifully. A special thanks to Dr. Bhushit Vaishnav sir, Head of the Academic Services PRL, for his dedication, effort, and coordinations that helps bring this event his life seamlessly. Our sincere thanks to Professor P.C. Vinod Kumar sir, President of IAPTRC 7, and Professor K.N. Joshipura sir for their constant supports, guidance, and enthusiastic involvement throughout the program. We especially grateful to Professor P.C. Vinod Kumar sir for actively participating in the questions answering and their facilitating segment. A special thanks to Dr. Chitan Limbachia, Head of the Applied Physics Department, MSU Baroda, for his warm and gracious introduction of the speakers. Our sincere appreciations goes to our IAPT 7 team for their tireless collaborations and commitment toward the making this lecture series grand success. Finally, a big thank you to all participants present here in a persons and our online audience watching via YouTube. Your active participants' curiosity and engagement are what give the life to such events. We also thankful to everyone who helped us directly or indirectly in making this program as a success. Let us continue to celebrate and carry forward the vision of Dr. Vikram Sarabhai, who believe in us using science to help and improve society. Thank you once again. Thank you very much.